this is my term project for intermediate heat transfer class. So for my term project, I'm gonna focus on external flow and heat conduction with 1D heat generation. So the statement is when the submarines travel across the ocean, they experience some heat loss due to convection um, on the outer surface and some heat loss due to the conduction. So I'm trying to simulate this scenario by having a flat plate, and on the upper surface um, I will have some certain flow with different conditions, and on the other surface ideally we want to keep the temperature to be constant, ideally room temperature. um, so to make the problem less complicated and more feasible, we can make a couple assumptions. We can assume that we have uniform volumetric heat generation. We have uniform thermal properties within the plate and the flow. We have flat plates to assure that flow will start with laminar flow condition. We can assume that we have non-compression flows and no radiation heat transfer, so purely convection and conduction. So we will have a couple thermal properties that we use in this simulation. We have thermal conductivity of steel, density and specific of steel, um, as well as several thermal properties of the flow, um, free stream velocity, free stream temperature. Um, so for this scenario, for this simulation, I decided to use oil, water, and honey as three flow conditions we studying. So the reason behind having so many variable flow conditions and several um, length configuration is that we want to make sure that we have a good insight in laminar as well as turbulent flow. The procedure is step one to find we have to find the Reynolds and the Prandtl numbers. From the Reynolds and Prandtl numbers, we can find the heat transfer coefficient. Then from there, we can find the temperature distribution within the plate, and we can find the required heat generation, the average required heat generation by using the conservation of energy. So I will walk you through the EASE model that I have developed. So on this slide right here is where I define all the input properties of the plate as well as the flows. As you can see in here, we have several properties. So when I actually developed the EASE model, I realized that if we can figure out how to do the calculation of vectors of arrays instead of passing in singular values, it would be so much easier and faster to compute. right here is the calculation using the first plate, which is 0.1 meter, I believe. Um, we have the Reynolds number, and then from the Reynolds number we can calculate the Nusselt number. From Nusselt number we can calculate convective heat transfer coefficient. From the coefficient we can calculate, we can actually start calculating the convective heat loss due to external flow of oil, water, and honey. This right here is where we calculate the conduction heat loss. So at the last step is where we actually calculate the important part, which is the required heat generation within the wall. So the required heat being generated will be equal to the heat loss due to convection plus heat loss due to conduction. So the calculation using the second plate is exactly same as the first one. The only different thing in here is we have 1 meter long plate instead of 0.1 meter, and all the flow condition is still laminar, so we still use the same equation to calculate Nusselt number. So on the third plate configuration, we actually see some different. We will start having turbulent flows with water and oil. So you will see some change in like a more noticeable change. It's gonna be a bigger jump. So when we run the simulation, this is what we get. So it is pretty much what we expected. The required heat being generated with the honey flow is the lowest, and the required heat being generated with water flow is the highest. It's actually double the heat being required in the honey flow. It's pretty interesting. This is the graph of required generated heat versus flow conditions. So you can have a visualize on how they look like in real life. Not real life, but this is more like very ideal case. As you can see, on the very top is water flow heat generation, and on the bottom is the honey flow. And this graph right here agree with the with our result from the simulation. So yeah, and this is the temperature distribution within the 5-meter long plate. So when I run the simulation on the 0.1 meter and the 1 meter, they yield the same, pretty much the same trend. So I just have this one in here for the presentation. Thank you for watching my presentation.